Okay, so this is our next lesson, still continuing with the topic of complex numbers, and today what we're going to look at is looking at finding the nth roots of unity to start with. I'll explain what that is in a minute, and then we're going to go on and find the nth roots of any complex number. Now when we find both of these, what you'll see is when we draw them in an Argand diagram, there's actually quite an interesting property of drawing them on an Argand diagram. And that's quite often asked within exam questions to do with this. It's quite clever really and quite nice. And then there's also an algebraic property of the nth roots of unity. Right, so let's kick off first explaining what I mean by nth roots of unity. Let's start first of all with the cube roots of unity. What do I mean by that? Well, unity is just the number 1. Okay, so what I'm wanting us to find is complex number z such that z cubed is 1. So basically z is the cubed root of 1. Okay, you're probably realizing that there's one easy answer that we can come up with, which is actually a real number, which is z equals 1. How do we find the other two? Well, we could put it into our calculator as this cubic, or we can use the factor theorem to divide out the z minus 1. We find the two roots for this quadratic. So our other two roots are these. Okay, so the cube roots of unity. Remember, that can be asked in a question in words like that, cube roots of unity. So you need to understand what that means. It also could be asked in a question like that, and it also could be asked in a question like that. So you need to be aware of all of the different ways in which they can ask you to find this. Okay, so our three cube roots of unity are 1, minus a half plus root 3 over 2i, minus a half minus root 3 2 over I. Now here's the interesting bit. If we draw those on an Argand diagram, okay, let's have a look at what we get. We get this. Okay, now this is quite interesting. So if we draw them, okay, here is our real root on the real axis 1, and then when we draw the other two, they make this equilateral triangle. Okay, now what you'll find is all of the roots of unity, okay, we've just done cubed roots at the moment, all of them lie on a unit circle, so all of them have modulus of 1, okay, and we always get the one that starts here on the real axis, because for any nth roots of unity, one answer is always z equals 1, whether that's cubed roots, fourth roots, fifth roots. And then look at the others. The others are spaced equally around this unit circle by rotating around. For this particular one, you rotate by 2 pi by 3. Okay, 2 pi is all the way round, remember? I need to fit 3 of them in, so you rotate by 2 pi by 3. Okay, so when you're asked to sort of represent your roots on an Argand diagram, you can quite easily draw it to be quite nice and symmetrical like that, all on a unit circle like that. And what do you notice about these two answers here, this one and this one? What you'll notice with those is that's a conjugate pair. The reason it's a conjugate pair, remember back to solving equations, this is the equation that I'm solving. Okay, that is a cubic with real coefficients, so any complex roots to it must occur in conjugate pairs. Okay, now throughout this lesson there will be a number of sort of graphs and things to draw like this, so do pause the lesson, sketch that down, make sure you're happy with that. Use a ruler, use a pencil, use a compass as well, and just make sure that you notice that the circle that you draw is a unit circle, so it goes 1 there, it goes up to minus 1 here, and it goes 1 here, minus 1 here. That's what the examiner would be looking, sorry, that's I and minus I, that's what the examiner would be looking for if you were to draw that. Okay, if you need to pause it, please do. Right, let's go on to the fourth roots of unity then. Again, the question can ask it as find the fourth roots of unity. It could also ask it as solve this equation. Okay, have a think at what values or what answers are obvious to you. 2 obvious answers. Z is 1 and Z is minus 1. Okay, because for both of those, Z to the power 4 equals 1. Okay, So you get z is 1, z is minus 1. There's going to be two more. They're going to be complex. So let's factorise it. Here's our z is 1 and z is minus 1. The other factor is z squared plus 1. So if I solve that, I get my z equals plus or minus I. So my fourth roots of unity are 1, minus 1, I, and minus I. Okay, so let's draw those again on an Argand diagram. Here we go. This is what it looks like. So you can see again we're getting that same pattern. Here, for any nth roots of unity, we always start at 1 on the real axis. Because it's fourth roots of unity, we have 4 roots that we need to be able to fit in. So each one we rotate round by 2 pi is all the way round. I need to fit 4, so we rotate round by 2 pi by 4, which is the same as pi by 2, and that's what gives me, you can see 1 on the imaginary axis, negative real, and then round on the other one. So again, all roots have modulus 1, so they're on the unit circle, and this time we're rotating through 2 pi by 4 or pi by 2 to get the next one. Notice again, so the complex ones, okay, are a conjugate pair. Okay, so the complex ones are a conjugate pair, so that's I and minus I. Reason being, what's the equation we were solving? Z to the 4 minus 1 equals 0, a polynomial with real coefficients, so complex solutions, okay, must occur in conjugate pairs. Right, good mathematicians, we spot patterns, so we can now predict what the 5th and 6th roots of unity would look like. So you can make a quick sketch of these. Do pause this if you need to. 5th roots of unity. Again, look, we've got the first one is there on the real axis at 1. They always are. I've drawn my unit circle. I need to fit 5 of them in. So I rotate by 2 pi by 5 to get that one. Okay, this is a little bit out. These should be conjugate pairs. Can you see this one? Whoops. So you see that one and that one should be our conjugate pairs. All right, they're a little bit out in this diagram, but because they're complex solutions, they should be conjugate pairs, which means they are a reflection in the real axis of each other. Again, the same for the other ones. Let's have a look at the 6th roots of unity. Okay, 6th roots of unity. When you've got an even power, you always get 1 and you also get minus 1. And then the others occur in conjugate pairs. To get from this one here to the next one, we go round by 2 pi by 6, because there's 6 of them to fit in, around the 2 pi rotation. So we rotate by pi by 3 to get the next one. So in a minute, we're going to work out what these, some of these are. Okay, but what we're going to do, well, we're going to do that in a minute, but then we're going to take this knowledge and we're going to sort of move it on further to look at the nth root of any complex number, so not just the nth roots of unity. Okay, but important things to remember, these are really important things to note, so make sure you get those written down. The non-real nth roots of unity are in conjugate pairs, okay, and all of the roots are equally spaced around the unit circle, and they all start from 1 on the real axis, because you always get 1 as an answer for the nth roots of unity. Okay, right, so let's have a look at this general form here. Okay, now the reason I've given you this general form is this is actually given in the formula book at the bottom of page 17. It's given in this form here. Okay, now you'll see the method that I use. I don't really like these little subscripts of, you know, I don't really like writing it like this. Okay, I like to write them out as specific answers, all right? And I think the method that I'm going to show you to use, what's quite nice for the nth roots of unity is we can then take that method and we can move it on to find the nth roots of any complex number. Okay, so yes, be aware that it's on page 17 in the formula book. All right, just in case you forget. They've got it written in exponential form there. Remember, we've got a few different ways of writing complex numbers, and you have to be dictated by what the question asks you for. Right, I did mention there was an interesting algebraic property. Okay, so let's have a look at what that is. Consider the sum of the nth roots of unity. Okay, if you think about what's going on, you always get 1. Omega is the second root. To get round to the next one, what I'll do is I'll double its argument, which is the same as omega squared. To get round to the next root, omega cubed, etc., 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 all the way up to omega n minus 1, because I'm doing nth roots of unity. Now have a look at that. We're summing something. That should look familiar to the previous lesson. That is a geometric progression. You can see each, or geometric series, each term is a multiple of the previous one, okay, with my first term is 1. Think about what my ratio is. Well, my ratio is going to be omega. So we can sum that using our formula. Do you remember our formula we used? A times 1 minus r to the n over 1 minus r. Okay, so if I sub in my values here, a is 1 and r is omega, I get this. Now have a think of what I would if we were in class. I would say, what's the value of that? Okay, hopefully you've had a look at that. Remember, nth roots of unity, okay, are solving z to the n equals 1. If omega is a root, then omega to the n equals 1. What does that tell you about the numerator there? That's 0. So this is a useful property to remember. The sum of the nth roots of unity is equal to 0. Okay, so you can be asked to prove that in an exam question. It's not loads of marks, but I think that's the best method to use if you are asked to prove it. There is some more of a geometric method you can use as well. If you think about the nth roots, okay, then any of the complex ones occur in conjugate pairs. So when you add everything together, okay, they effectively end up sort of cancelling each other out, all right? So that's another way of thinking of it. But I think this, if you're asked to prove it, this is the best way to prove it. So do make sure you've got that written down. Okay, let's just do a couple of examples of those before we move on to the nth roots of any complex number. So, as I said to you, they can ask it in an exam question in a variety of different ways. Okay, they could say solve z to the 5 equals 1, or they could in words say find the fifth roots of unity. Okay, so you need to be aware that those both mean the same thing. Okay, now they've given me specific instructions that they want the answers in exponential form. Okay, remember what exponential form is, re to the I theta? And they specifically have said they want the argument here to be in the pi convention, so argument range of values minus pi to pi. Okay, now the method I'm going to show you, you might think it's a little bit tedious for this, but the same method works, okay, when we find the nth roots of any complex number. So I'm finding the nth roots of 1. So first I'm going to write that in exponential form. That's e to the I times 0. Okay, now I know I need 5 answers. And we also know that if one answer is this, I can get my next answer by adding 2 pi to my argument. Okay, so I am going to do that enough times. I'm going to keep adding 2 pi to my argument until I have got myself 5 answers, because I want 5 answers. Okay, so I know my first answer is going to be 1, and I know that's e to the I times 0. And then here's my 1, 2, 3, 4, 5 answers. Okay, now let's think about what happens if I fifth root. You know, in exponential form, we did it last time, if you fifth root, then you fifth root the modulus and you divide the argument by 5. Okay, I'm going to leave 1 as 1. The modulus of this is 1. Okay, so all I'm going to do is take my argument and divide it by 5. So that one that one. So this is what I'm doing to fifth root. Okay, so these are my answers, but my examiner has been particular to do with the range of values of the argument. So I'm going to need to adjust these. Okay, so this one's fine. 1 is fine, or I can write it as e to the I0, that's fine. This one's within the range of values. This one's within the range of values. Okay, I need to sort this one out. But if you think about 6 pi by 5, well, that's going to be round here, isn't it? So that's pi, and that's an extra pi by 5. So with that convention, reading it round here, that's going to be e to the minus 4 pi by 5. And again, this one is 8 pi by 5. So if you think about that, that's pi, okay? And then it goes round by 3, so it'll end up down here. So that's all the way round, okay? And that's going to be 2 pi by 5 there. Okay, so it's e to the minus 2 pi by 5. And what you can do is take away 2 pi. That's another way of thinking about it, if you want to, rather than drawing the diagram. Okay, so that's my answers. So that's that one done. Okay, right, let's do another one. Okay, so find an exact form of the 8th roots of 1. So 8th roots of unity. So remember what I'm doing, that's the same as solving z to the 8 equals 1. Okay, so let's write out our answers. 1, which is e to the I times 0. So what I need to do is I need to add 2 pi, but I need to get 8 answers. Okay. So lots of answers, 1, 2, 3, 4, 5, 6, 7, okay, and then my last one, 8, e to the I 14 pi. So now I'm going to do the 8th root of those. So remember, for the unity ones, the modulus is always 1, so I don't need to worry about that. So I take each of these and I divide by 8. So I get e to the I 2 pi by 8, e to the I 4 pi by 8, e to the I 6 pi by 8. I know these simplified, but I'm not going to bother. Okay, e to the I, well, we'll write that as e to the I pi, e to the I 10 pi by 8. Okay, e to the I 12 pi by 8. And e to the I 14 pi by 8. Okay. Right, what did my question ask for? My question asked it for this form here, so a plus bi. I don't need to show any working for this. I can use my calculator. Do you remember how to use your calculator? You use the R, angle, theta button. Okay, so my first one is 1, that's fine like that. For this one, you're going to type in, R is the modulus, so you're going to type in 1 angle 2 pi by 8. Okay, do make sure you're in radians and make sure you're in complex numbers mode. And that will tell you you've got root 2 over 2 plus root 2 over 2i. Okay, you're going to do the same for the next one. You might work out what that actually is, but just use your calculator if you're not sure. That comes out to be I. Type in the next one and you get minus root 2 over 2 plus root 2 over 2i. You get minus 1. Okay. You get minus root 2 over 2 minus root 2 over 2i. Make use of your calculator, that's what it's there for. You get minus I and you get root 2 over 2 minus root 2 over 2i. And I'll put brackets calculator. So notice all of our complex solutions are in conjugate pairs. Okay, where's the conjugate pairs? Well, that's one there and one there. Okay, there's another one there and another one there. And then there's I and minus I. So they're all in conjugate pairs. And if you were to draw those, they would all be equally spaced around the unit circle. Okay, right. Let's go on to then, which is usually what the exam questions ask for, which is the nth roots of a general complex number. But what's good about this is we will take our method that we've used already and we will apply it to finding the nth roots of any complex number. I always like to have a method that I can use for any types of questions. So any nth roots questions we're going to do in the same way. Okay. So if you think what we need to do when we find the nth roots of any general complex number is I need to find one root, okay, and then the others will be placed symmetrically around a circle, okay. Now it won't necessarily be a unit circle, it depends on the modulus of the roots that you get, okay. How are we going to find the modulus of the roots we get? We know that if we're solving, you know, z to the n equals sort of, you know, a plus bi, or if we write it as re to the I theta, we know if we nth root the modulus. What do we do to the argument? We take the argument and we divide it by n, okay? And then in the same way as what we were doing in the previous ones, we're going to do that, and then we're going to add on our 2 pi, okay, and then divide through. Okay, now what you've got to think about here is, will the complex roots occur in conjugate pairs? It depends. It depends on what this original equation here was that we were solving. If we are, say, finding the fourth roots of 2 plus 3i, then that is a polynomial, but it has some complex coefficients. So they don't necessarily occur in conjugate pairs. It really depends on what the original one is that you're solving. Okay, so we've got 3 examples to do for this. So let's crack on with our first example. So solve the equation z to the 4 equals minus 16. First thing to think is, will my complex roots occur in conjugate pairs? Well, yes, because that's the same as solving z to the 4 plus 16 equals 0. Okay, so it's a polynomial, but I've got all real coefficients. Right, let's do the same method that we did before. So I'm solving z to the 4 equals minus 16. Do you remember before what we did was we wrote the 1 when we were doing the roots of unity, we wrote 1 as e to the I0. So I need to write that in exponential form. The modulus of it is 16, okay, and the argument is pi. So if you think about where minus 16 ends up on the Argand diagram, it's here, okay. So its modulus is 16, but its argument is pi. If you're not sure, okay, you can type that in complex number mode, and then you can press the r theta option, and it will tell you that its modulus is 16 and its argument is pi. What did we do before? I need 4 answers. So what I do to get each of my other answers is I add 2 pi to the argument. But notice what's happening here. We're starting with this argument. So when I'm adding 2 pi, I've still got a 16, but I will get 3 pi. Okay, so that's 1 answer, 2 answers. Okay, that's going to be 5 pi. And that's going to be 7 pi. So I am adding 2 pi onto my initial argument. Okay, now what I'm going to do is I'm going to fourth root. You have to be careful with this, because not only do I divide the argument by 4, I fourth root the modulus as well. It's a common thing people forget. So fourth root of 16, that's quite nice. If it does end up as a third, leave it as a third. So I fourth rooted 16 and I've divided the argument by 4. I fourth rooted 16. I've divided that argument by 4, by 4th rooted 16 and divided that argument by 4. And again, I 4th rooted 16 and divided that argument by 4. Okay, so what you're doing is make sure you remember that this is the 4th root. Okay, and then you divide the arguments by 4 like we did before. Right, now the question does not say anything about how to produce your answers. There's no range of values for theta, anything like that. It doesn't say in a plus bi form or exponential form. So those are perfectly valid answers. Okay, they're using the 2 pi convention. Put them on an Argand diagram. Okay, now we know what they look like. They will be spaced around a circle. What's the size of the circle? Well, each of my answers has magnitude 2. So you're going to use a compass. I'm sorry, this is going to be a little bit rubbish, but you will use a compass, you will draw your circle, and you will make it really clear that it's of modulus 2. So that's going to be 2i, and that's going to be minus 2i. Okay, make sure you put them roughly in the right place. So my first one has modulus 2 argument pi by 4. So it's going to be out like that. So that is my first one, okay? Now, if you look at these, they go round by 90 degrees. So do make sure when you draw them in, use a ruler, they will actually sit opposite each other like that, won't they? So make them nice and, you know, like they look like they should, and they've got 90 degrees between them. What I would say is I would label nice and clearly which one's which. So that's number 2, that's number 3, and that's number 4. And because we know what they look like, okay, we can draw in our circle and we can actually make our Argand diagram look pretty decent. Pencil, ruler, compass though, please. You'll notice they are conjugate pairs as we expected. The reason they're conjugate pairs is because this was the original equation we were solving, okay, which has got all real coefficients. Right, next one. Okay, that looks a little bit different. Okay, so because we've got a z cubed in it, and then we've got a complex number, we're going to use our method that we've got here. So what the equation is that we're solving is z cubed equals minus 4 root 2 minus 4 root 2i. So that's going to be the cubed roots of that complex number. Now remember, the first step we want to do is convert it into exponential form. So use your calculator, type in minus 4 root t minus 4 root 2i, and do the r theta button, and you'll get 8e to the 13 pi by 4i. Okay, use your calculator. You're allowed to. Okay, we need 3 answers because it's a cubed root. So here's my first one, 8e to the 13 pi by 4i. How do I get the next one? I add 2 pi to this. I add 2 pi to this, okay? Use your calculator if you're a bit rubbish with fractions. If I add 2 pi to that, then, no, that's right. Then I get 8, still modulus 8e to the 5. Oh, I've written the wrong, I've misread my, sorry, apologies for me. I've misread that. That should be a minus, I bet you were all shouting out there. That should be a minus 3 pi by 4. Okay, so this first one here should be a minus 3 pi by 4. All right, so I'm taking minus 3 pi by 4, sorry, that was me misreading, minus 3 pi by 4. I'm adding 2 pi to it, and I get e to the 5 pi by 4i. I'm adding 2 pi again, and I get e to the 13 pi by 4i. I'm sorry, my writing is really awful on here. Apologies for that. Okay, so how do I get these answers then? 2 things to do, remember. Cube root the modulus and divide the argument by 12. So cube root the modulus, divide the argument by 3, so I get 3 pi by 12i. Cube root the modulus, divide the argument by 3, 5 pi by 12i, cube root the modulus, divide the argument by 3, 13 pi by 12i. Okay, and again, the answer hasn't really asked for them in any particular range. I suppose at the moment we do have a slight variety in range here. In fact, we've got a -1 and then we've got one more than pi. So I guess we should be consistent really. Okay, so let's simplify that argument as well, because it does cancel to 2e to the minus pi by 4i. So that would be neater. Let's leave that one as it is. Okay, and then with this one, if we take 2 pi away from it, we'll get 2e to the minus 11 pi by 12i. So at least that gives us all of our answers in the pi convention. Okay, usually, to be honest, an exam question would say what convention to use. Okay, one more to do then. What I'd like you to do is to pause this and for you to have a go at that. All right, so it's a wordy one. It says find exact expressions for the fourth roots of that. So what you are solving is z to the 4 equals that. Okay, -8 root 3i. Okay, so pause it and have a go. Right, what do we do first? We make it in exponential form. 16e minus 2 pi by 3i. Use your calculator. Okay, use the r theta option on your calculator. Okay, what do we do now? We take that as one of our answers, or one of our answers before we fourth root, and we add 2 pi successively until we get 4 answers. Use your calculator if you want. So if I add 2 pi, remember what you're adding 2 pi to. You're adding 2 pi to this to get your next one. Okay, so that gives you your 4 pi by 3. That gives you 10 pi by 3. Okay, so I'm adding another 2 pi, one more. Oh, I've gone purple, never mind. 16 pi by 3. What do I do now? Okay, well, to get z, 2 things. Fourth root the modulus. Well, fourth root of 16 is 2. Divide the argument by 4. Okay, e to the minus 2 pi by 12i. Fourth root the modulus. Divide that by 4. Fourth root the modulus, divide that by 4. Fourth root the modulus, divide that by 4. Okay, let's have a look at the question. Right, question wants them in a plus bi form. That's okay, our calculator will do that for us. Okay, so put these into your calculator. You put this one in. This first one, you put it in as 2 angle minus pi by 6, and it will tell you what the complex number is. It's root 3 minus I. The next one, again, put in 2 angle 4 pi by 12, you get 1 plus root 3i. Next one, minus root 3 plus I. And the next one, minus 1 minus root 3i. Okay, we don't have conjugate pairs. Why don't we have conjugate pairs? Because the original equation we are solving is z to the 4 equals -8 root 3i. And that has some complex numbers as coefficients, so we're not expecting conjugate pairs. Argand diagram, you'll have more room than me. Okay, but let's draw it like that. Now it's always equally spaced around a circle. Circles size 2, because the modulus of all of them is 2, so make sure it's nice and clear. That's 2 minus 2 minus 2i, 2i, real and imaginary. Okay, and they'll be equally spaced round, but we don't, remember with these nth roots of complex numbers, we don't start on the real axis, we start at the first one. So what's the argument of that? Minus pi by 6. Well, minus pi by 6 is going to be something, you're going to use a nice straight line and a ruler, it's going to be something like there. So that's number 1, and that refers to that one. Okay, we've got 4 of them. Remember what happened before when we had 4 of them? They are diagonally opposite each other and sort of make a cross. So do make sure that your answers look like they have 90 degrees between them. Okay, so this one, if I just use red for that so you can see, so this one is my number 2, there. This one is my number 3, which refers to this one, and this one is my number 4, which refers to this one. So do, when you draw them on, the examiner would expect you to indicate which one is which, and goodness, you'd use a pencil, a ruler and a compass, so it would look so much better than mine. That is so awful, but never mind. Right, questions for you then. Okay, exercise 1F page 24. Do all of those questions, please. The only ones I want submitting are 6, 7, 8, which are exam questions. I want those submitting on Teams, please, by Thursday, the 11th of June, so I can have a look and mark those. Okay, if there's anything you didn't quite understand, just rewind and go and watch it again. Otherwise, good luck with those.